Assalamu alaikum everyone. We are group on. Our project title is Post Disaster Surveillance and Response Using Human Detection from Real-Time Aerial Imagery. In this project, we have explored possibilities of efficiently handling post-disaster rescue through human identification from aerial imagery. Objective of this project: the drone will be flown to an affected area and surveyed using the onboard camera. Secondly, using the camera feed, operators will determine the situation and act accordingly. Our workflow: making a drone that can move and hover steadily with a mounted camera and some other payload. Drone mounted wireless camera transmits a video to the base station. The drone will patrol and scan for humans. Python program running on the laptop scans the video to detect the humans. If humans are detected, the operators will be notified and rescue operation dispatched. Drone will be guided as it is instructed to the next search area.
Our project is divided into two parts: the base station with the Python script and the image detection algorithm connected to the base station transmitter, which sends data to the drone when the UI is used or any button on the keyboard is pressed. And on the drone, there are 4 motors and their drivers, the electronic speed controllers and the propellers to provide lift. On the flight controller board, there is a gyroscope, which is the main feedback sensor, radio module for receiving commands, and the Arduino microcontroller, which is the brain of the drone. Below that is a battery and the camera placement. And now we explain how our communication takes place. There are two-way communication available in our project. First, the drone is controlled from the base station by operating the user interface. The UI can take commands from both the buttons as well as the keyboard, which is sent to the base station radio module using serial communication, which further relays the command using the radio communication to the drone. And now the drone uses the commands to fly accordingly. At the same time, the drone-mounted camera uses a different communication protocol to send live image back to our base station. This communication module uses a different channel, such as Wi-Fi for mobile cameras and FPV for any other small cameras. Finally, the base station applies image processing to our live feed to detect humans in distress in the area the drone is in.
Here we discuss the balancing mechanism of our PID algorithm. As we can see, any aircraft has 3 degrees of rotation, so a 3D PID must be implemented to keep the drone stable and hovering. In our case, the GY521 gyroscope provides the closed loop feedback of the roll, pitch and yaw angles. The Arduino MCU does the math and the motor speeds are adjusted accordingly to keep the drone stable. In order to rotate in any particular direction, 2 motor speeds must be encouraged while the other 2 is decreased as shown in the diagram. By default, the set points are at 0 degrees, but when a movement is desired, the set points are set at a particular angle, roll, pitch or yaw to achieve that motion.
Here in our base station we can send and receive signals using serial communication. Here we can see live feeds with real-time human detection and also send commands like forward, reverse, yaw right and left, hover, etc. to control the direction of the drone. The drone speed can also be controlled by varying throttle. Thus, different PID parameters can directly be controlled and useful information like roll, pitch, values and each motor speed can be extracted from here. For human detection, various algorithms perform satisfactorily including YOLO V325, PedNet, Multiped, SSD MobileNet V1, V2 and SSD Inception V2. The deciding factor in these types of emergency situation is the detection speed and accuracy. Among these models, YOLO models are comparatively faster and the latest YOLO V5 algorithm is the state of the art in this field in terms of optimized accuracy and latency. Among different versions of YOLO V5, the 5S is one of the fastest and better performing. So initially we started with the pretend YOLO 5S version. YOLO V5 is mainly a CNN based architecture suitable for object detection tasks with the help of bounding boxes. It consists of 3 parts: backbone, CSPD darknet, NEC, PANET, and head YOLO layer. The data are first input to the CSP darknet for feature extraction and then fed to PANET for future fusion. Finally, YOLO layer outputs the detection results like class, score, location size, etc. Although pre-trained models work pretty good, in almost all scenarios, custom training boosts overall performance.
At first, pre-trained YOLO V5S model was used, but it had a diminishing result with higher heights. In order to make our drone suitable to fly at different levels according to our task, we wanted a more robust detection approach. So to increase detection accuracy, we custom trained the model. In our case, a post-disaster dataset would have been the perfect fit. But due to scarcity of suitable datasets of that sort, we have compared among various datasets including CrowdHuman, VizDrone and Okutama Action to train our model. Among these, the VizDrone dataset is chosen to train our human detection algorithm as it covers most of the cases with height differences and background variation, which will be crucial in identifying humans from post-natural disaster footage. From the detected images, it can be seen that the model performs pretty well in close-range detection even with the pre-trained weights, but training for 10 epochs and 30 epochs has shown significant improvement in performance. But unfortunately, for vertical images taken from very high altitudes, the accuracy tends to drop a lot. In those cases, training for more epochs will prove to be useful, as with more epochs we see improvement in performance.
Are some possible extensions for our project. Our drone has good lifting capability. In addition to a small camera, it can also lift small mechanical or air-dropping devices, possible to carry out humanitarian aid or relief operations with increased range. Also, our drone has a software integrated, so various surveillance tasks can be carried out or image detection algorithm can be easily modified to suit the current scenario or task. And here are some challenges we faced during this project. As the drone is big, it is currently very difficult to balance it with a properly built chassis and with a huge load like the phone camera. So for practical applications, FPV camera must be used. Due to large chassis and propellers, the gyro sensor was vibrating too much, which made it harder to stabilize. Therefore, we have acquired less footage to show in our hardware. For better performance, a PCB board and balanced motors must be used. To prevent an accident, safety features are added to shut the drone down if the command from base station is disrupted. IP camera currently has very limited range, which needs to be increased for practical usage. Time to see our system in action. First, we run the software. We can incorporate these sliders to tune the motors and balance the quadcopters over lift in case it is unbalanced. And the PID values of roll, pitch and yaw can be changed easily from this software. We can also start or stop the quadcopter from here. Once the PID tuning has been done using these sliders, we can use the throttle to speed up the quadcopter or slow it down. Also, we can do this using our keyboard. Our camera feed will not show anything right now as it is not connected to a camera. Now let's see the communication process. We can start the motor using the keyboard. You can see the motor has started, and by pressing W we can see that the throttle is increasing and the drone will start to fly off. Pressing off instantly shuts down the motors.
Now we will show some test runs of our drone in the open field. Due to many difficulties, we could not manage to capture one perfect run, and so we will show several clips demonstrating different functions and some challenges we faced along the way. Here we can see the drone increasing its throttle speed and taking off, but the command sent from the controller was not being able to control the direction of the flight. So the drone kept flying leftwards until we decreased the speed and it landed. This is a similar trial as before. The throttle speed was not enough to attain more altitude, but the drone hovers for a good amount of time in the air. In another trial, the drone flew up to a much higher altitude than before. As we can see, the drone will now attain some altitude. Unfortunately, we were not able to properly land it, and it crash landed in this and several subsequent trials. In the next clip, we can see our group member trying to balance the drone while it was correcting itself using PID. But due to vibration, our gyroscope was generating garbage values, and the PID corrections were being extreme in one direction at one time and then in another, which is why it was constantly proving difficult in earlier and later trials to balance the drone in flight. Here is a video of the drone taking a little flight and then landing safely again. Here is a similar video
where the drone takes a little flight up in the air and then lands at a different location. We will now show some clips highlighting the key difficulties that we face. In this test run inside the room, our drone takes a flight and then loses control mid-air and flips over. This happens in several trials and causes some damage to the propellers. In the next clips, we can see the drone simply hovering over the ground, as we can see here, and not gaining altitude. In the next clip, in the open field, we can see a similar issue. The throttle speed is increasing at this moment. The drone is hovering over the ground, but there isn't much altitude. The key reason behind this was that the arms weren't vibrating too much and the gyroscope was not generating steady voltage. Also, the throttle speed at the trials were not enough to lift the heavy weight of the drone. This is another reason why we could not sustain a camera from it to take video clips, as it would further cause imbalance.
Here we are demonstrating our camera feed. As we have seen earlier, more epochs give better results. So we are using the 30 epoch weight for our camera feed live action. Here we can see that the model is detecting pedestrians and other classes effectively, though some mismatches still persists. Still, the bounding boxes are not stable. As the frame changes, the detection accuracy varies. For real-life implementation, we'll need more stable and robust detection method. We have discussed in our theory section how to do that. But overall, we can see from here that our model is performing satisfactorily to be used in real-life scenarios. Here we can see a real-life application of our model. As we have told before, our model can't capture high altitude classes from the images. Here we can see that there are pedestrians available there, but we can't detect properly them. But cars and other big classes can be easily be classified. The messy background is obstructing our judgment here. Here is another case that all the pedestrians are not counted properly. But overall we can see that comparatively the 30 epoch weight performs way better than the 10 epoch and pre-trained model as expected. So we are hoping that training for more epoch will give us better results. Also we can use YOLO or trans-TFS or YOLO with attention head so that our model performance can improve. Here again the messy background is obstructing lower cases like pedestrian, as we cannot identify human features from this angle. But still the 30 epoch one is performing quite good enough in identifying pedestrian from these images. Here is a comparatively less messier situation, but still the problem persists of high altitude. In low altitude we can detect humans, but in the front side of this car the humans are gathered together, so the human feature like hand or face were not perfectly calculated. In this shot it can detect properly, but here we can see that the bounding boxes are coming and going, so we can decide that the detection accuracy is changing with frames.
Overall, our system has a flight range of 1 to 2-story building, which can be extended further later, and the system can detect humans in real life as expected. Thank you very much for your kind attention.